This lecture is about inductive definitions and judgment and inference rules. Suppose that we'd like to design a programming language. We can have infinitely many different programs. We have a program 1, we have another program 2, and so on. So we can have infinitely many different programs given a programming language. But the specification of the programming language itself is finite. So this is a specification of the programming language, or the definition of a programming language. So this is finite, and we can have infinitely many different programs. So therefore, there should be some way of generating these infinitely many different programs from a finite description. There should be some mechanism. And this mechanism is called inductive definition. Basically, we'd like to specify the syntax of a programming language with a finite specification according to these inductive definitions. And then from this syntax or the specification of the programming language, we can generate many different programs. So let's first talk about inductive definitions of syntactic categories. So in order to design a programming language, you have to give syntax first. With this syntax for your programming language, you can, for example, implement a parser. And using this parser, you can, for example, accept a valid program, or you can reject an invalid program. So there should be some parser here in order to design and implement a programming language. So the first step in designing programming language is to formulate its syntax. And the syntax of a programming language usually consists of several syntactic categories. So for example, the definition of a programming language might have expressions or types and patterns and so on. So these guys are called syntactic categories. And let's talk about a simple example of a syntactic category called natural number. We'd like to define a syntactic category describing set of natural numbers. Unlike mathematics, where natural numbers start at integer 1, in computer science, natural numbers actually start at 0. So this is the inductive definition of syntactic category nat. So we write nat as a shorthand for syntactic category natural number. So this is the syntactic category, and syntactic category nat n is defined as either 0 or successor of n. This is the inductive definition of syntactic category nat. So nat stands for natural numbers. So this is the name of syntactic category, and this is called non-terminal, in the sense that its expansion has not terminated yet. So this non-terminal n is defined as, this symbol is red, is defined as. So natural number n is defined as either, so this symbol, vertical bar, is red, or So natural number n is defined as either 0, this is just the character 0 that is intended for natural number 0, or successor of another natural number n. So this symbol S that stands for successor. So this is an inductive definition of syntactic category net intended for natural numbers. And the reason that this definition is inductive is in the middle of defining a non-terminal n, we are permitted to use the very non-terminal that is being defined. So this is the definition, the actual definition of non-terminal n or syntactic category net. But in the middle of defining this non-terminal n, we are permitted to refer to the very non-terminal that is being defined. So it is inductive. So here are examples of natural numbers that can be produced according to this inductive definition. First, natural number n is defined as either 0. So 0 is definitely an example of natural number according to this inductive definition. Now we have the first instance of a natural number. Now let's use the second branch in this definition. So according to this definition, if n is a natural number, successor n is also a natural number. So successor of n, successor of a natural number. But we know that 0 is a natural number, so let's substitute 0 here. So according to this inductive definition, successor 0 is also natural number. Let's use the second component in this definition again. So now we have successor of something, and this should be another natural number. And previously, we have generated this natural number, successor 0. So let's substitute this one, successor 0. So we have generated another natural number, another instance of a natural number. So in this way, we can generate infinitely many natural numbers from this finite description. So this inductive definition is finite in size, but we can generate infinitely many different natural numbers. So here's another example. Let's try to define trees, binary trees of natural numbers, trees. So the way that we give this inductive definition is, we first write the name of a syntactic category, tree. So this is the name of a syntactic category, tree, and this time we use non-terminal t. So tree t is defined as either leaf of n, where n actually refers to the previous syntactic category net, or internal node consisting of a natural number n and left subtree t and right subtree t. And in this example, the inductive definition, this one, refers to another syntactic category defined earlier. And in the second branch in this definition, we see two instances of the same non-terminal. So this t can be any tree that complies with this inductive definition. And the second t can be another tree that is valid according to this inductive definition. And keep in mind that even though we use the same non-terminal symbol t, that does not mean that the left subtree, this one, and the right subtree must be identical. It simply says that here you can substitute any tree that is generated according to this inductive definition. And here you can substitute another binary tree. And these two binary trees do not have to be the same. So here's an example of binary trees generated according to this inductive definition. First, let's use this one, diff of some natural number. And previously, we have generated this sequence of natural numbers. So let's use this 0. So diff 0 is an example of binary tree according to this inductive definition. Now, let's use the second component in this definition. So node, here we expect some binary tree, and here we expect a natural number, and here we expect another binary tree. So let's substitute this one, leaf 0, and here we have to provide a natural number, so let's use 0. And here we have to provide another binary tree, which does not have to be the same as this one. So for example, leaf of successor 0 is also another valid binary tree because you can substitute any natural number here. So we could use this one. So in this example, the left binary tree and the right binary tree are not identical. So this is another example. Now let's talk about mutually defined inductive definition. So the idea here is that we can inductively define two syntactic categories which are mutually related to each other. So here's an example. We'd like to define two syntactic categories, even for even numbers and odd for odd numbers. So this is the name of the syntactic category, and let's use non-terminal E. And this is the name of the second syntactic category, odd, and let's use non-terminal O. And if we think about the definition of even numbers, you can give this definition. E is defined as either 0, because 0 is always an even number. For everything else, an even number is going to be a successor of another odd number. So we can use this definition, successor of odd number. And what about odd number? If we think about the definition of odd numbers, every odd number is always the successor of another even number. So you can have successor of even. So for example, according to this part of the definition, 0 is going to be even number. And now according to this part of the definition, successor of E, where E is going to be replaced with this 0, this is odd number, this is even number. Now we have the first instance of odd number, so we can generate an even number using this component of the definition. So successor of odd, and for this odd number, we'd like to use this one, so successor 0. So this is the second even number that we have generated according to this mutual definition. And we can keep generating even numbers and odd numbers on and on, like a successor, successor, successor 0. You substitute this one over here, and you generate the odd number. So we can actually list the entire set of even numbers and odd numbers in this way. And we say that this syntactic category E for even numbers and O for odd numbers are subcategories of syntactic category NaN, because every element in this syntactic category even belongs to this syntactic category NaN, and also every element in this syntactic category odd belongs to NaN. So in this regard, we can say that this even and odd are subcategories of natural number syntactic category NaN. The last example of syntactic category deals with strings of matched parentheses. So let's first define a syntactic category parent, which stands for just a strings of parentheses. So for example, this one, or this is also string of parentheses. This is a string of parentheses, and this is a string of parentheses. So let's first define a syntactic category parent for strings of parentheses. So parent S with non-terminal S here, S is defined as either epsilon. Epsilon stands for empty string, where no character is found. So parent S is defined as either epsilon for empty string or left parenthesis followed by another string, because if the string is not empty, it must start either with this opening left parenthesis or closing right parenthesis. So this is an easy definition of strings of parentheses, whether it is matched or not. So there is no constraint on the use of parentheses. This belongs to parentheses. This belongs to this parent. This belongs to parent. This also belongs to parent. This also belongs to parent. Now, the interesting question is, we'd like to define a subcategory of parent where the parentheses are matched. So in other words, we'd like to define a subcategory, let's say n parent, for strings of matched parentheses. So for example, this string of parentheses is matched, but this is not, because this one has no corresponding closing parentheses. So we'd like to define a subcategory n parent for strings of matched parentheses. So this is the first attempt. So n parent S is defined as either empty string, and if this string S is matched, perhaps we can have a pair of parentheses, left one and right one, and then we can put another string of matched parentheses inside. Then perhaps this is matched. In other words, if this guy is matched, this one is also matched. Or we can concatenate the two strings of matched parentheses. Let me use a dot here to indicate that these two guys are concatenated. So this is actually a valid definition. For example, according to this definition of n parent, we can show that this string is string of matched parentheses, because this one is perhaps a valid string that belongs to n parent. Then according to thanks to the second component in this definition, the whole string also belongs to n parent. So this is fine, but Not every subcategory is equally powerful or equally expressive as another one. In the case of M-parent, there's nothing wrong with this definition of syntactic category M-parent, but one problem is it is ambiguous in the sense that a given string of matched parentheses can be interpreted or can be decomposed in several different ways. So here's an example. Let's just say we have a sequence of triple pairs of parentheses. One way to decompose this string, according to this definition, M-parent is the first pair followed by the two pairs. So this one is going to correspond to the first S here, and this one is going to correspond to the second S here, non-terminal S here. But that's not the only way. Another way to decompose this sequence of parentheses is take the first two pairs and then concatenate it with the last one. So in this case, the first two pairs correspond to the first non-terminal S, and this one corresponds to the second non-terminal S. So there's nothing wrong with this definition of M-parent. It is a valid definition for syntactic category for strings of matched parentheses. But one thing that is slightly unsatisfactory is it is ambiguous in this sense. So we can try to identify another subcategory of parent for strings of matched parentheses, but this time we'd like to have an unambiguous definition. Unambiguous syntactic category that is equivalent to M-parent, but it is going to be unambiguous. So let's use the syntactic category L-parent, and this L-parent is going to be a subcategory of a parent. This is a subcategory of a parent, so it's going to be just a sequence of parentheses, and it is matched. It's going to be string of matched parentheses, so therefore this L parent is going to be equivalent to M parent. But unlike M parent, it is going to be unambiguous. And it requires a bit of thinking, but it is a good exercise actually. So if we think about an unambiguous way of specifying strings, then it must be defined as either empty, or if this string is matched at all, then the first symbol must be an opening left parenthesis, otherwise it's not going to be matched. So here we have this left parenthesis. And if the whole string is matched, then we must have a corresponding closing right parenthesis somewhere. So we are going to have this right parenthesis. And in between these two parentheses, these two symbols, there must be another string of matched parentheses. If this is not matched, then the whole string is not going to be matched. And optionally, this string can be followed by another string of matched parentheses. If this one is not matched, then the whole string is not going to be matched. So if we think about this problem, we can come up with an alternative definition of strings of matched parentheses, but it's a huge improvement over the previous one, M-parent. This is ambiguous, and this L-parent is not ambiguous. So the lesson here is that two syntactic categories can be shown to be equivalent to each other, But that does not mean that all these syntactic categories are all unambiguous. As we have seen in the previous examples, it turns out that M parent and L parent are equivalent. But this one is ambiguous and this one is unambiguous. So we can put more thought to the problem of defining a syntactic category. Then you might be able to come up with a better solution. Now let's talk about inductive definition of judgment. Inductive definition of judgment. So the first question is, what is judgment? So far, we only discussed the syntax, how to specify the syntax of a programming language, and the answer is we give inductive definitions of syntactic categories. And these syntactic categories can use another syntactic category in this definition, or they can be mutually defined. But in order to discuss the design and implementation of a programming language, we should be able to actually state the properties. So for example, if successor n is a natural number, then n is going to be a natural number. This is a fact about the syntactic category net. We can think of a net as a very simple programming language. And this is a property about this programming language called net. And this is not about syntax. This time we are talking about properties of this programming language called net, or syntactic category net. So therefore, we should have some way of stating properties of syntactic categories or stating facts about syntactic categories. So we use judgment to state the properties. So judgment is simply just an object of knowledge, that's all. Object of knowledge. And you might have a proof of this judgment. In this case, it's provable, and it becomes a part of our knowledge. It becomes part of our knowledge. We know it. But depending on the judgment itself, we may not be able to prove it, or the judgment may be unprovable. Then we do not know it. So we can say that with the proof, we know the judgment, because the judgment is an object of knowledge. So with the proof, we know it. But without proof, that's not provable, and we do not know it. So here's an example. 1 minus 1 is equal to 0. Is this judgment? Yes, it is judgment because it expresses a certain piece of knowledge. And moreover, it is provable. So it is a part of our knowledge. We know that 1 minus 1 is equal to 0. What about 1 plus 1 is equal to 0? Is this judgment or not? It turns out that this is also a judgment. It's an object of knowledge. But this time, we cannot find a proof of this judgment, unfortunately. So perhaps this is not provable. So even though this is a valid form of a judgment, we never know it because we don't have a proof. But still, this is judgment. What about this statement? It is raining outside. It is an object of knowledge. Depending on the situation, this judgment might be worth a lot of money. And in some case, we may have a proof of this judgment, so it is provable. But in other cases, we may not have the proof, so it is not provable. So to summarize, judgment is just an object of knowledge, like 1 minus 1 is equal to 0, or 1 plus 1 is equal to 0. And we may have a proof of it, in which case we know it's provable. Or we may not have a proof of this, in which case we do not know it. That's judgment. Now the question is, how do we prove judgment? Let's go back to this first example. We know that this is judgment, but how do we prove this judgment is true? How do we present a proof of this judgment? For this example, we automatically think the arithmetic that the elementary arithmetic that we learned from primary school. So we can say that this judgment is provable. But what is important here is this arithmetic, the rules for adding integers or the rules for subtracting, multiplying, dividing integers, this arithmetic is not given for free. You have to actually state explicitly that in order to prove this judgment, you may use this arithmetic. But the point is that to prove a judgment, you should have something like arithmetic. In order to prove this judgment, you should have something like arithmetic, which is not given for free. For this particular example, everybody happens to know what kind of rules we should employ, which is arithmetic. So the question is already answered. But in general, for every judgment that you present, you have to provide corresponding rules, and these rules are called inference rules. So, for example, to prove this judgment, 1 minus 1 is equal to 0, we automatically recall the arithmetic rules. But these arithmetic rules are the inference rules that we are permitted to use. So to be strict, when we are asked to prove this judgment, we should actually ask for corresponding inference rules, which are arithmetic in this example. So to summarize, judgments are just objects of knowledge. If they are provable, we know them, but some judgments may not be provable. In that case, we don't know them. And in order to prove a judgment, you have to provide something like arithmetic. And this arithmetic is just a set of inference rules. So we use these inference rules to prove judgment. Let's see the syntax for writing inference rule first. So inference rule. The way that we write this inference rule is we write this horizontal bar and write judgment below this horizontal bar. And this judgment is called conclusion. And above this horizontal bar, we list several judgments. And these judgments are called premises. And optionally, we could write the name of the inference rule here. So this is the name of the inference rule. And what this inference rule means is that if judgment J1 through Jn hold, then by applying this inference rule, we can show that the conclusion J also holds. So for example, when you have proofs of all these judgments in the premise, you apply this inference rule, and then you have proof that the conclusion J also holds. So that's the interpretation of this inference rule. This is the inference rule, and this is the interpretation. As a special case, we might have empty premise, in which case we have an inference rule of this form, judgment J and inference rule. Here, so we have no premise. And this form of inference rule is called the axiom. The meaning of axiom is self-evident rule. So this is self-evident because the premise is empty. It doesn't require any further evidence necessary to prove the conclusion, judgment J. It's just self-evident. It's automatically, immediately evident. So we say that a special form of inference rule with the empty premise is called axiom. So here are several examples of inference rules. First, M equals to L and L equals to M, then, so this is the first judgment and the second judgment as premises, and then we can deduce M is equal to N. This is equal to N. And this inference rule states the transitivity of equality of natural numbers. So we might decide to use this name trans. And here's another example. M is equal to L, then M plus 1 is equal to L plus 1. And you could give an appropriate name here. And this inference rule states the property that if two natural numbers are equal, then their successors are also equal. So these are examples of inference rules. And here's an example of an axiom. So here's an example of an axiom. N is equal to N itself, and we might choose name EQ, which states that an integer is equal to itself, or reflexive. So this states the reflexivity of equality. And what about this one? 0 is a natural number. This is an also axiom because the premise is empty. So to summarize, we can introduce several forms of judgment, but without corresponding inference rules, these judgments make no sense. In other words, every time you introduce new notion of judgment, you have to provide the corresponding inference rules so that you can try to prove this judgment according to these inference rules, or you can refute this judgment according to these inference rules. By refuting, you show that the judgment is not provable. So for example, when you introduce a new judgment of this form, equality between natural numbers, this is a new form of judgment because with the proof, it increases our knowledge. Then you have to provide corresponding inference rules, in which case it's going to be arithmetic. Now let's see how to apply inference rules to build a proof of judgment. So here's an example. Let's introduce n net. This is a new form of judgment, which stands for n is a natural number. But remember that for every judgment that we introduce, you have to provide the corresponding inference rules. Otherwise, this judgment makes no sense. because there is no way to prove or refute a judgment. So this is judgment. Now you have to provide inference rules. These are the inference rules. First, we have an axiom. 0 is a natural number. Let's call it rule 0. And let's introduce another inference rule for successor. So if n is a natural number, then successor n is also natural number. So we have the new judgment, a new form of judgment, and its corresponding inference rules. Now we can try to prove a judgment of this form, or we can try to refute a judgment of this form. And note that here, this n is actually called the meta variable. We do not intend to n as the final string, not to be expanded. So in other words, here we are not saying that something that looks like a successor n is a natural number. This is a meta variable which can be expanded into another sequence of strings. It's just a placeholder. It's just a placeholder to be expanded later. So for example, if later we somehow shows that successor 0 is net, if this is the conclusion of this inference rule, then this meta variable n is going to be expanded into this one. So in this sense, this n is a meta variable to be expanded later. We are not saying that this one, successor n itself, is a natural number. Now, we have this judgment and net for n is a natural number, and we have these inference rules, these two inference rules. And let's compose these inference rules to prove this judgment. At this point, we know that this is judgment, but we don't have a proof of it. So we do not know it yet because there's no proof. Now let's try to build a proof of this judgment. So in order to prove this judgment, the successor 0 net, if we go back to the set of inference rules, perhaps you'd like to apply this inference rule first. So according to this inference rule, in order to prove this judgment, you want to prove successor 0 net instead. So by applying this inference rule backward, the problem of proving this judgment reduced to proving this judgment. So the problem has been simplified somehow. And then, similarly, in order to prove this judgment, you apply the rule successor backward again, and then the problem reduced to proof of 0 net. Now, in order to prove this judgment, you only have to prove this judgment. Now it's time to apply this axiom 0. So we have 0 net. Now the proof is complete because this is an axiom. It does not require any further evidence. So this one constitutes a valid proof of this judgment. And we say that this is derivation tree. It looks like a tree where the root is in the bottom. This is the root of the derivation tree, and this is the leaf. In this particular example, there is a single leaf. Here's another example. Let's introduce two judgments, even and odd, and even and odd. So this judgment and even means that n is an even number. And this judgment means that n is an odd number. So remember that for every judgment you introduce, you have to provide corresponding inference rules. So you have to have inference rules. Otherwise, this judgment makes no sense. And the question now is, what are these inference rules for these two judgments? So we'd like to actually translate the previous definition of syntactic categories, and we can obtain three inference rules. The first is 0 is even. This is 0 even. And if n is odd, then successor n is even. This is a successor even. And finally, if n is even, then successor n is odd. This is successor odd case. So we have this set of inference rules. We have judgment and we have inference rules. So now we are ready to actually prove the judgment. So let's prove successor 0 is indeed even. This is a valid form of a judgment, but at this moment we do not know it. It's not part of our knowledge because we don't have a proof. So let's try to prove this judgment. We apply this inference rule, successor E. Now the problem reduces to proof of successor 0, this is successor 0 of odd. And let's apply this inference rule backward, successor odd. Now we have, in this case, this meta variable n is going to be this 0. This one is the same. So 0 even should be proven. But this is immediately obvious because we have this axiom. So this derivation tree constitutes a valid proof of this judgment. Now, thanks to this proof, this derivation tree, this is a part of our knowledge. We know that this judgment is actually true.